All right, we're starting chapter 2 of the geometry textbook. Chapter 2 is concerned with parallel lines. So everything we're going to study here is going to have some relationship to parallel lines. In this video, we're going to go through the opening section, which is on the parallel postulate and special angles. Okay, so in the previous video, we reviewed exactly what is meant by parallel lines, the definition of parallel lines. So what it means for two lines to be parallel, two or more lines. So take a look at that video if you need, just to refresh your memory on what we talked about in chapter 1. Okay, so here's the opening image. It says, breathtaking, the widest cable-stayed bridge in the world, the Leonard P. Zankum Bridge, also known as the Bunker Hill Bridge, lies at the north end of Boston, Massachusetts. Lying above the Charles River, this modern design bridge was dedicated in 2002. Cables for the bridge are parallel or nearly parallel to each other. Yes, you can see that, right? The vertical towers above the bridge are perpendicular to the bridge floor. In this chapter, we consider relationships among parallel and perpendicular lines. Thanks to the line relationships, we can establish a most important fact regarding angle measures for the triangle in section 2.4. Another look at the Bunker Hill Bridge suggests the use of symmetry, a topic that is given considerable attention in section 2.6. Okay, so these, you can see definitely you've got these parallel cables here, pretty cool, and these towers here are perpendicular to the bridge floor. And so we're going to consider relationships among parallel and perpendicular lines. And with these relationships, we can establish an important fact regarding angle measures for triangles in section 2.4. And then also we can see there's a symmetry about this bridge, and we're going to look at the use of symmetry in section 2.6, a use of symmetry, or how symmetry can be used. So, okay, perpendicular lines. By definition, two lines or segments or rays are perpendicular if they meet to form congruent adjacent angles. Yes, we learned that's the definition of perpendicular. Not that it's not 90, they meet to form, two lines meet to form 90-degree angles, two lines or segments or whatever to form 90-degree angles. That's the 90-degree angle constraint is comes as a result of the definition of perpendicular, but that's not part of the definition of perpendicular. It's that you have two lines or segments or whatever, and they meet to form these adjacent angles that are the same. They're congruent. And as a result, it ends up being the case that they are perpendicular. They're 90 degrees. But it's if you extend one of these lines, or I guess the top line, if you extend the top line, if you make it like there's an intersection and it goes all the way through and the line doesn't change direction or anything, then it's also ends up being the case that the other two adjacent angles are also congruent and right angles as well. That has to be the case. You couldn't have two lines intersecting going all the way through each other and have one side have congruent adjacent angles which means they're perpendicular, but the other side is something different than that. That couldn't happen. We talked about that. Like this couldn't be, this is 90 degrees, this is 90 degrees, but this line continues through without, it stays a line, continues through, and then this is 120 and this is 60. That couldn't happen. So, okay, but that's the definition of perpendicular. Two lines meet or segments are raised to form congruent adjacent angles. Using this definition, we proved the theorem stating that perpendicular lines meet to form right angles. That was a theorem, not a definition, because that was a result of the definition. We can also say that two rays or line segments are perpendicular if they are part of perpendicular lines. So yeah, to me what they're saying there is something like if we have something like this, ray A, B, and then maybe segment CD. Okay, well, if you want to be really technical, you could say these aren't perpendicular because they don't intersect, but if you think about these as lines, then you could sort of say that in a roundabout way, say that, look, segment CD is perpendicular to ray AB, because the lines that they're on that extend infinitely are perpendicular by the technical definition of the meaning of perpendicular. We now consider a method for constructing a line perpendicular to a given line. So we already did this kind of construction in chapter 1, where we took a line segment and we wanted to construct a perpendicular to this line segment, and not necessarily a perpendicular bisector, or this is just a line, but I mean, we could think about a line segment too, but we wanted to construct a perpendicular at any point here. So we picked a point X, set the compass radius to like a certain value, like maybe when you put the center of the compass here, and then maybe and set the radius to something like comes out here, then drew an arc out here, flipped sides, didn't change the radius, drew an arc out here. Then we didn't technically have to change the radius of the compass, but we did just to show that it didn't matter, that we could if we wanted to. So we changed the radius of the compass, increased it a little bit, then put the center of the compass here and drew an arc like that out, and drew an arc out here. That didn't change the center or the radius, put the center of the compass here, drew an arc out here. And then from that intersection, if you draw a line to that point X, that meant the line was perpendicular. These two lines were perpendicular. So that was a construction there. So now we want to do another construction, another method to construct a line that's perpendicular to a given line. Oh, from a point not on the given line. So this is going to be different. Previously, we did the construction where we were dealing with a point that was on the given line, anywhere on the given line. Now we're looking to construct a perpendicular that goes through a point that's not on the given line. So, okay. So we want to construct PQ to where PQ is perpendicular to line L and Q is on line L. So, okay, with P as the center, open the compass to a length great enough to intersect L in 2 points A and B. Okay, so with the center at P, open the compass to where it can intersect A and B, or any 2 points on the line, like at both ends of the line. Oh, okay, but we're going to draw one arc. So, okay, you wouldn't want to put the center of the compass here, or the radius of the compass here, because then when you drew it, you would, right, you would get this. It would only intersect at 1 point. So you want to make it big enough to where you can intersect it at 2 points. Any of these would work. Okay? So then you draw an arc going through 2 points. And then from there, with A and B as centers, mark off arcs of equal radii to intersect at a point Q. Okay? So then what they're saying is, so here we got the center at point P, and then let's say we drew that arc AB, then I guess you could choose any radius you want. It doesn't matter. You could change the radius if you want again, so I'll do that. You could come to points, like that's fine. We'll do this radius. And then you draw an arc out here, but now don't change the radius of the compass. Come to point B and draw an arc here, and then where those intersect, that's okay. Point Q is not on the line. It's P and Q are off the line, but then R will go through the line. But this would have been point Q, and that's the perpendicular. So that's interesting. These would be perpendicular. I mean, with those constraints, that means that these two lines are perpendicular, at least within the uncertainties of the compass, right? But still, that's pretty good. That's pretty cool. In this construction, angle PRA and PRB are right angles. Greater accuracy is achieved if the arcs drawn from A and B intersect on opposite lines, on opposite the side of line L from point P. Construction 6 suggests a uniqueness relationship that can be proved. Cool. So later in the course, we're going to come back to the different constructions we've done and see why they're true. Why what we just did ensures that, at least within the uncertainties of the compass, right, and how precisely at the points we put the center, that these two lines are perpendicular. Okay, theorem. From a point not on a given line, there's exactly one line perpendicular to the given line. All right, this was similar to a theorem that we had read about. If you have a line, then if you think about just one point on that line, then there's only one unique line that goes through that point that's perpendicular to the line. Like you can't draw, here's point X, you can't, this is point X, that's on point L. We can't draw two separate lines going through point X that are perpendicular to line L. That's what they're saying. And in a similar way, we can't draw, going through line P or point P here, we can't draw more than one line that's going through point P that's perpendicular to line L. There's only going to be one line that's one unique line that goes through point P, any point off the line, and it's also perpendicular to the line. So the term perpendicular includes line ray, line plane, and plane plane relationships. Okay, in Figure 2.1c, ray RP is perpendicular to line L. Okay, the drawings in Figure 2.2 on page 69 indicate two perpendicular lines, a line perpendicular to a plane and two perpendicular planes. So, okay, we'll take a look at that in a second. Let's read what it says here. Parallel lines, just as the word perpendicular can relate lines and planes, the word parallel can also be used to describe relationships among lines and planes. However, parallel lines must lie in the same plane, as the following definition emphasizes. So, okay, we started with looking at perpendicular lines in this opening section here. So now let's come to the next page and take a look at, so okay, here's two perpendicular lines, but you could also think about the idea of perpendicularity with lines and planes and planes and planes. So line L is perpendicular to plane P in this case, and the way you can think about that is a plane contains an infinite number of lines, right? And so assuming that, ignoring any lines within plane P that are skewed to line L, because then it's not really relevant, as long as they're not skewed to line L, then any line in plane P is going to be perpendicular to line L. And that's the idea of how you can think about that line L is perpendicular to plane P. Okay, now you could have two planes that are perpendicular as well, and it's the same idea that any line in plane R and plane P, as long as they're intersecting in some way, are going to be perpendicular. So the entire plane R is perpendicular to the entire plane P. Okay, so that's perpendicularity. Now we're shifting focus to the idea of parallel lines, but also we can think about parallel lines parallel to planes and planes parallel to planes. So, okay, parallel lines are lines in the same plane that do not intersect. All right, well, we talked about this in the previous chapter, and also we reviewed this idea in the previous video. So, yeah, it's two lines that there's a unique plane that contains the entirety of both of those lines, and those lines never intersect. And you want to distinguish that from skewed lines, which are two lines that never intersect, but there's no unique plane that contains the entirety of both those lines. All right, more generally, two lines in a plane, a line in a plane, or two planes are parallel if they do not intersect. Figure 2.3 illustrates possible applications of the word parallel. So, yeah, like perpendicularity, you could have, so two lines are parallel here. There's a unique plane that contains them, the plane of the computer screen. Now, you can also think about this line and this plane are parallel because they never intersect, right? For their infinite lengths. Planes extend infinitely in all directions as well. And so for their infinite size, they never intersect. Now, you can think about that with a line and a plane, there's no idea of skew. With lines and planes, either they intersect, so they're not parallel, or they don't intersect, which means they're parallel. Okay? And then similarly, you have two planes can be parallel, means they never intersect, but there's no skewness with two planes. Either they intersect, that means, and they don't intersect, or they don't intersect and they're parallel. What I'm trying to say is there's no idea of with a line and a plane or two planes that if they don't intersect, maybe they don't intersect in such a way that it's not considered parallel. No, not with lines and planes. Okay. In figure 2.4, two parallel planes, M and N, are both intersected by a third plane, G. How must the lines of intersection A and B be related? Okay, so what they're saying here is that you've got two parallel planes, M and N, and both are intersected by a third plane, G, but it doesn't say anything like G is perpendicular to M and N. It just says they intersect. G intersects M and N. So what does that mean that there, if anything, that there is a relationship among the lines A and B? Because when two planes intersect, they form a line. Well, okay, if you think about it, that means A and B are going to be parallel. Because by definition of two planes being parallel, that means there's no lines, because a plane contains an infinite number of lines. There's no lines in the two planes that will ever intersect. So, okay, if we think about this, yeah, let's come back here to try and think about this. So, okay, we've got two planes that are parallel, which means that means the planes contain, a plane contains an infinite number of lines and points. So any two lines that you pick, one from this plane, one from this plane, aren't going to intersect. That's what makes the planes parallel. So does that mean that if we pick a line from each plane that those two lines are going to be parallel? No, not necessarily. Even though there's no skewness, you don't think about two planes can be skew, but no, you could pick a line that's in this plane like this, and a line in this plane that's like this. Those two lines are skew, right? Because you can't get a unique plane, one unique plane that contains both of those lines. Okay, and in the same way over here, we can think about, yeah, this line and this plane are parallel, but that doesn't mean that every single line contained within this plane is going to be parallel to this line. Every single line won't intersect, but it might not be parallel, it might be skew. This line is skew with line R. Or you could make a line that's parallel in the plane as well, right? And not just one line that's parallel, you could make this line is also parallel. It's a different plane. These two lines would be contained in this plane, but these two lines would be contained in this plane. Okay? So now, all right, but if we come back to the original question here, we've got these two parallel planes. That's fine. But then we've drawn a third plane that intersects both of those planes, not necessarily in a perpendicular way. So does that additional fact there give us some information about line A and B? Well, that means A is parallel to B. Line A is parallel to line B. So yeah, okay, that's the parallel notation. If we want to indicate intersection, we say that, so R intersect S is there's the zero set, empty set. There is no intersection. R intersects T there's no intersection. T intersects V, there is no intersection. Here we would say that, so A is parallel to B. Well, okay, let me start here. You would indicate that, so okay, they give us that plane M is parallel to plane N. Okay, now we would say that the intersection of G with M is equal to line A, and the intersection of G with N is equal to line B, which I believe we could do this. We could say G intersecting with all of plane M and N, which is M in union with N, is equal to A, all of line A and all of line B, right? Because like A union B, if this is A, this is B, maybe they intersect, maybe they don't. Well, actually they don't. So this is A, this is B, because there's no intersection with A and B. But A union B is all of this and all of this, right? So you could write it like that, but the consequence is that A is parallel to B. Why is that? Because the two planes are parallel, M and N. That means you pick one line from any line you want from plane M and any line you want from plane N. They will not intersect 100%. But whether or not they're parallel or skew, you don't know. But if you add a constraint that you have a plane slice through both of the planes, well then, in that case, you've picked two lines what have you done? Now you've got, with the intersection of two planes, you have a line. So you have a line from one plane and a line from another plane. They don't intersect 100% because the planes are parallel. Okay? But also now in this case, those two lines are contained in the same plane. Now that's the definition of parallel. You see? All right, Euclidean geometry. The type of geometry found in this textbook is known as Euclidean geometry. In this geometry, we interpret a plane as a flat two-dimensional surface in which the line segment joining any 2 points of the plane lies entirely within the plane. Whereas the postulate that follows characterizes Euclidean geometry, the perspective on applications section near the end of this chapter discusses alternative geometries. Postulate 10, the Euclidean parallel postulate, is easy to accept because of the way we perceive a plane. Okay, so let's make sure we understand this, what they're saying here. The type of geometry that we use in this textbook is Euclidean geometry. And this geometry, it's saying a main principle is that we interpret a plane as a flat two-dimensional surface in which the line segment joining any 2 points of the plane lies entirely within the plane. Okay? And so now we're about to read a postulate that characterizes Euclidean geometry. So that's what we're about to read. But the perspective on applications section near the end of this chapter discusses alternative geometries outside of Euclidean geometry, okay? So this next postulate here, the Euclidean parallel postulate, is easy to accept because of the way we perceive a plane, as just described. Okay. The parallel postulate, through a point not on a line, exactly one line is parallel to the given line. Okay? So, again, what is this saying here? We've got a line L, and if we pick a point not on that line, then there's going to be one unique line through this point that's parallel to line L. So it would be something like this. And we can't draw another different line that's also going through point M that's also parallel to line L. That's what they're saying. And this postulate works because they're saying that this postulate is easy to accept that seems intuitive because we're thinking of from the perspective of Euclidean geometry, whereas we interpret a plane as flat, perfectly flat two-dimensional surface in which any 2 points within that plane, if you join with a line, are entirely within the plane. But later in the chapter, we're going to look at an idea from the perspective of another type of geometry. Okay, but that's the postulate, which is easy to accept because of this Euclidean perspective. Consider figure 2.5 in which line M and point P both lie in plane R. It seems reasonable that exactly one line can be drawn through P parallel to line M. The method of construction for the unique line through P parallel to M is provided in section 2.3. Okay, yeah. Here's line M, and they have this point P here. Now, if you're going to have two lines that are parallel, there's going to be a unique plane, so they go ahead and draw that plane first. There's going to be one unique plane, one unique parallel line going through point P. A transversal is a line that intersects two or more other lines at distinct points. All of the lines lie in the same plane. In figure 2.6, T is a transversal for lines R and S. Angles that are formed between R and S are interior angles. Those outside R and S are exterior angles. Okay, so yeah, this is important here. So we got, what is a transversal? Let's read this again. A line that intersects two or more other lines at distinct points. All of the lines lie in the same plane. So, okay, you have a transversal is a line, and it's going to intersect two or more other lines at distinct points. So let's think about what that means. So they're not saying that if you have, let's say, okay, here's line T. It intersects line R, and let's say you erased line S, and this was line S. It was like on top of line T. Well, it intersects. Yeah, I guess it intersects line S in that case, but it's not at one distinct point. So they're saying that this line T is going to intersect two or more lines at distinct points on those lines. Oh, and also you could maybe say, oh, this is line S. Erase line S and make that line S. Well, then those 2 points that it intersects are not distinct. Or no, okay, also would be a case where you could do this. There's line S, erase line S. Is that a transversal? Those 2 points aren't distinct. So it needs to intersect two or more lines at distinct points. All right, now, but furthermore, all of the lines involved need to be in the same plane. So, in other words, you couldn't say that. So, okay, we've got, here's a line here, they intersect, and now you've got going kind of into the page, this line here, right? Kind of like the X, Y, and Z axes. They intersect, they're going in different directions. You can't make one unique plane that contains all three of these lines. So there's no transversal here. Now, if you did have something like this, well then, yeah, you could call, okay, we've got line L, M, N, P, okay? But if line M, N, and L are all in the same, you could make one plane that they're all in. Well, then in that context, L is a transversal intersecting lines M and N. But line P is not involved. It's like so here's the plane that contains L, M, and N. If you rotated 3D space to where you're viewing straight at the plane, you could see lines L, M, and N. You could see something like this. Okay? Now, notice it doesn't say anything about the lines needing to be perpendicular or parallel. None of that matters. But like line T and S could be parallel, and it would still meet this definition of a transversal. All right, angles that are formed between R and S are interior angles. Those outside R and S are exterior angles. So between the two lines here, the two crossing lines, those are like interior angles. Angle 3, 4, 5, and 6, you call those interior angles. And then outside of R and S, 1, 2, 7, and 8 are exterior angles. Okay, and so from the perspective of, let's say all three of these lines were actually, or all four of these lines were actually in the same plane, even though it's hard to, maybe you could visualize that. Well, then, like, these angles would be in kind of, I guess, it just depends on how you look at it. These would all be interior with respect to M and N. Well, no, because between M and N, P wouldn't be involved. You'd have to go like two lines at a time. So with respect to, so L is a transversal here with respect to lines M and P, and if they're all in the same plane now, I'm assuming P is now, they're all in the same plane. L is a transversal with respect to M and P with these interior angles and these exterior angles. But with respect to P and N, these are interior angles, these are exterior angles, etc. With respect to M and N, these are exterior angles, these are interior angles. So, all right, consider the angles in figure 2.6 that are formed when lines are cut by a transversal. Okay, yeah. Two angles that lie in the same relative positions, such as above and left, are called corresponding angles for these lines. In figure 2.6, angles 1 and angle 5 are corresponding angles. Each angle is above the line and to the left of the transversal that together form the angle. So if you have angles that are in the same relative positions relative to the transversal and their respective lines. So you have the transversal that's intersecting line R here. So if you, okay, at the top left, you have angle 1, but the transversal intersects line S here. At the top left, you have angle 5. So they're the same relative position relative to the transversal. So those are called corresponding angles. Angles 6 and 2 are corresponding. 8 and 4, and 7 and 3 are corresponding. Okay? Now, two interior angles that have different vertices and lie on opposite sides of the transversal are alternate interior angles. Two exterior angles that have different vertices and lie on opposite sides of the transversal are alternate exterior angles. Both types of alternate angles must occur in pairs. So, okay. Two interior angles that have different vertices and lie on opposite sides of the transversal. So, okay, we're thinking about all of the interior angles here. 3, 4, 5, and 6. What are alternate interior angles? Well, we're focusing on the interior angles. They have different vertices, but they lie on opposite sides of the transversal. So here's all the interior angles. They have different vertices, and they lie on opposite sides of the transversal. So 3 and 6 are alternate interior angles. 4 and 5 are alternate interior angles. In the same way, you can do the same thing with the exterior angles. Different vertices, opposite sides of the transversal. So 1 and 8 are alternate exterior angles, and so are 2 and 7. Okay, and so it's going to be important for us to memorize this notation here regarding transversals and the lines they cut across and the corresponding angles, because these types of situations are going to come up a lot in geometry in the problems in this course and in real life. And so we're gonna study relationships among these angles. One is, you can see we've got vertical angles here, which we know are congruent, right? Vertical angle pairs, but there's more relationships we can establish. And so you need to understand the way these are named and the notation, so we can, whenever you solve problems in the course and in the real world, you'll know, okay, this angle is an interior angle. Its alternate interior angle is this. So what's the relationship among those two? And you could just figure out, okay, these two they're add to 90, or they add to 180, or they're congruent. You could easily just go through and identify the features of all the angles. All right, we'll continue with this section in the next video.